Okay, question 4. We've got a question about radioactivity. Radioactive tracers, so a really common question. Tracers come up a lot. An isotope is injected into the bloodstream. The isotope emits radiation. As the blood flows through the kidneys, this radiation is detected outside the body. So they're giving you a clue. What type of radiation travels from the kidney to the scanner? So there's my body, there's my kidney. I need radiation that can penetrate outside of the body. So alpha and beta are just not going to do it. It'll have to be a gamma source. During the technician, they need to take readings for about 30 minutes. The half-life is going to be about 6 hours. Explain why 6 minutes is not suitable. So it's the idea that it's going to decay, and by the time we actually get it into the patient doing its stuff, there's going to be so little radiation we won't be able to detect it. So the isotope would decay too quickly to give an activity or a level of radiation to measure. You can word that any way you want, but an activity. Explain why a high isotope of about 6 days is not suitable. So it'd stay in the body too long and it would increase the patient's dose or risk of disease. So we have a sweet spot in terms of too short, I won't be able to measure it. Too long, it's going to be in the body too long. State 2 ways of reducing the radiation risks. So this is a common question, comes up a lot. So any of the following, the technician could use lead shielding, and I could say they could wear a lead apron, or they could go into a room that's got lead shielding. Limit the time of exposure, increase the distance from the source. As I said to you, the dentist will clear off out of the room along with their person helping them. They could wear a lead apron and masks, or another common one that comes up is wear a radiation dosage meter or badge, so they can see how much radiation they've been exposed to. Any 2 of those. Okay, next question, we've got a nuclear reactor, so we've got nuclear fission, and we've got various things going on, but it says explain how pushing the control rods further into the reactor, so we know these move up and down, and I'm going to now push them down. Explain how it slows the nuclear chain reaction. So the idea is these control rods made out of boron, and they can absorb neutrons, and because of that it controls the chain reaction. So we just got to put that into sentences. So the control rods absorb neutrons, mark there for that key word. So there are less neutrons available for the chain reaction, and therefore I could say we reduce the rate of fission. Okay, next part. The moderator in the reactivity slows the neutrons so that the neutrons are more likely to start fission reactions. So we know the neutrons have to have the right velocity. It then tells us the speed of fast neutrons and slow. And it says calculate the average speed of the slow as a percentage of the fast. So that's just telling us the ratio. So we need to have slow over fast. There's my ratio. And I want a percentage, so I'm going to have to times it by 100. So take the slow, divide by the fast, times 100, and we get that answer there, 0.013%. The nuclear reaction is the first stage of the process. Describe how energy is transferred from the nuclear reaction to the next stage. So we've got our nuclear reactor here. There's our reactor. We're going to have a heat exchanger here, which could just be some water pipes. And the crucial part is we're then going to heat water to turn it into steam so that it can turn a turbine, which can turn a generator. So that's the link from nuclear fission to then making an alternating current. So now we've just got to put that into words. So a small amount of mass is lost and converted to energy according to equals mc squared. Or we can say the daughter nuclei and neutrons have kinetic energy. And then our next part is capture this in water, turn it to steam. So this is transferred to thermal energy in a heat exchanger or a coolant to then heat water to steam. And that's that question done.